All right, so we're going to talk about the next thing to talk about in this context of MIM, which is after having made these things with these wonderfully round spheres, how do we go about debinding them? And this is something of a good opportunity because of the nature of MIM particles makes it really obvious when these phenomena are going on. So rather than a bunch of broken rubble like ceramic injection molded particles, we have these nice round particles, and it's very easy to illustrate certain things. And what basically you can see theory before your eyes because everything's round and perfectly shaped, which is exactly what theoreticians love. So this is helpful in terms of trying to illustrate some of these concepts. So this is should sort of reinforce some of the things we talked about previously and make it more obvious. And what I want to first show you is some data from a lab we had a few years ago. And this involved making, first off, nucleation and growth of nanoscaled zinc oxide, which you can do via a chemical process. And we would fabricate this powder and then compact it into 4-point bend test bars, and then do a Weibull modulus determination on this. And the lab had some issues, but what I'm showing you here is a series of specimens, and the difference between the top and the bottom portion, I'm not sure exactly where that line is, but it's in this area, is this was 0.25 weight percent starch. And this was just regular ZNO down here, the nanoscale. All right, and so not much starch. First off, it's starch, which sounds like a very boring thing. But then, as you've already seen, this industry uses things like beeswax. So starch is right up their alley as far as additives. And so this is a reasonable additive that was added to this to try to provide some additional strength during the compaction process. And as you can see, and this was, the heating rate was also, which is very important, 2 degrees C per minute. All right, and so not extremely slow, certainly not extremely fast though. And so what you see here in this upper portion, first of all, the lower portion looks fine, and this was, I should also point out this is going to 500 C. Not very high temperatures, just enough to burn out the organic, more or less. That was the whole point of it. And then we'd switch to a different furnace and complete sintering in a different furnace. And so what happened here is that this relatively small amount of starch at a reasonably slow heating rate, even though all those things were combined together, part of this is driven by the fact that this is nanoscale ZNO, so that really, really tiny particles. So you took that starch and you dispersed it amongst some really, really tiny particles that have some really, really tiny pores. And think about Knudsen diffusion and how slow that is and all those good things happening. And so rather than just sit there and make nice rectangles like we got here at the bottom, they all blew up. And it's sort of, it's like the pages of a book. It kind of blew up in layers, all right? And so these are the compaction forces being counteracted by the expansion and the force flow of the gases coming out of this pretty small amount of starch. All right, and so this is way shy of what we're talking about for CIM or MIM, where it's like 25% organic. This is only 0.25% organic. All right, so it shows you that if you don't control things correctly, and this heating rate is obviously too fast, and what we ended up doing in the rest of the lab was we stopped using starch because we could still make squares, rectangles that were suitable. And so this is a great example of failure to remove most of the binder prior to sintering and what happens. And these are obviously a bunch of rubble rather than the desired 4-point bend specimens. And so that's what we're trying to avoid here. And of course things are worse because, again, we're dealing with a lot more organic. But of course things are better because we're dealing with much larger particle size. Nothing's nanoscaled here. And we also have much more regular geometries to work with. And so part of what makes this successfully function, along with not heating it too quickly, and along with not having the nanoscale involved in any significant way, is capillary forces in this context. And so we have to remove the, we have to remove the binder without disrupting the particles, and in many cases this can be done in multiple steps. and we're going to talk about some of those multiple steps. But in MIM, the parts are heated, the binder softens, and if heated too quickly, the part itself is unable to withstand the stress from gravity, temperature gradients, or internal pockets of force flow. And that's what you just saw, an example of force flow that was not being regulated. So if we'd had the ability to apply a lot of pressure to those zinc oxide components, which we don't, then we could have counteracted all that pressure, and it would have been forced to come out through the available spaces, even though that would have been pretty slow. But anyway, so with that last part is what we're talking about in terms of the previous slide. But we still have to deal with the fact that these are heavy metal particles, all right? Gravity acts on them very efficiently if they're 9 grams per cc, okay? And so temperature gradients that can show up in these systems, especially when there's a lot of poorly thermally conductive binder holding everything together, all right, all these things have to be taken care of. But what we can also think about is if the pores are partially open, and so we talked about this a little bit when we referred to the mixed binder systems in the last lecture, these capillary forces can be used to resist distortion as the binder softens. And so first off, we'll talk about this equation, which is F sub c, the capillary force holding beads together. All right, and so this is just thinking in terms of these nice, theoretically perfectly round particles, which it turns out we have in the context of metal particles. That force is equal to the pi times the liquid surface energy, so you might make that gamma sub L. And then also in the numerator is the particle diameter. All right, and so we can get relatively large capillary forces when the particles themselves are relatively large. And so what you're seeing here, and these are actually not metal particles, but the story's even better. These are glass beads, and they're pretty large. They're 700 microns or so. And what you've got is a layer of glass beads sitting in between 2 glass slides, and we put some water in there, all right? And it's just the magic amount of water. So I hope you can see these from where you're sitting. You've got these nice, first off, round points of contact with the glass slide. All right, those are all capillary forces making pendular bridges and holding these beads very tightly to the glass that we're looking at these things. And you also have the same type of pendular bonds between the glass particles themselves, all right, holding everything together. All right, and so what I want you to take away from this is that this is kind of the goal state for a lot of MIM. And we only get to this goal by removing the space between the beads up to the point at which these necks are formed. But we need these necks to stay there. All right, so what we're going to be talking about is MIM that uses this strategy, which we injection mold with an easily removed organic phase, and then we also have in there an organic phase that is not as easily removed. Okay, but it gets to this point where the bridges are a certain size and they can exert F sub c's that are relatively large and hold everything together. Is that clear? Is this image clear? And so what we'd end up doing is progressive stepwise removal of binder. So we remove one part of the binder system and leave the other behind. And we use this to then retain the shape of the overall component as a result. Okay, so we're dealing with these large, heavy particles. They're round. They have no mechanical connection to each other, any more than a bag full of marbles has a mechanical connection to itself. All right, they'll just roll if you give them a chance. So hopefully that's clear. All right, so early binder practice. Related to thermal degradation alone, as you've heard already, you could have up to 300 hours for a complete binder removal, and longer than that if the parts are big and thick and fat. All right, very complicated because something that's thick, you have not just one environment, you have a variety of environments inside that thick piece, and that complicates and slows everything down. In many cases, they used only single combinant systems and neutral debinding atmospheres, which greatly prolong the debinding cycle. Today, however, we can achieve debinding in as little as 2 hours, and so we've talked about some of those processes, the force flow, where you add an additional pressure to it, but we also designed the binder system to make this overall process more efficient. For some small components, and we're talking pretty small. Debinding is incorporated heating. The sintering temperature is not necessarily a multi-step process. All right, so sometimes when things are tiny, diffusion distances are small, and the binder can come out without really damaging the part. But these types of improvements, even for the small parts, are catalyzed by an improved understanding of the debinding processes and also polymer design. We haven't talked much about this. You know, I've been throwing polymer names at you. And those names are associated with what we know about different polymers. So polypropylene, very familiar, everyone works with it. But there are polymers out there that we don't have the names of, mainly because the companies who make them are not going to let you know what they are. All right, so if I want to publish a paper here at OSU, I'll use polypropylene. But if I work in industry, I would find one of these expensive polymers and work with those. And that's very important. So we can have polymer chains that include oxygen. All right, why would we want oxygen in there? Yeah.
Helps them break apart easier.
Helps it what?
Break apart easier.
Yeah, so we have the ball bearing approach, so things can rotate more easily around those ball bearing areas. What else does oxygen allow for us to do? But if you think about as a polymer breaks down, what will it help make? CO2 or carbon monoxide or gas that can come out. A relatively small molecule, not a hunk of polymer chain, just a small molecule that can come out and diffuse away relatively easily. So there's good reasons to have oxygen in there. We do know, however, that oxygen in the furnace atmosphere can attack the polymer, all right, but for certain powders, oxygen may alter the final polymer chemistry in undesirable ways, and so we can make epoxides and things like that end up turning into carbon. And so what's often used in industry is customized binders that greatly simplify or cheapen the debinding cycle. Okay, whoops, I didn't want to do that. Let me go back to where I was, if it'll let me. There we go. Okay, if we want to, oh, now they're totally separated from each other. Wonderful. So what we do is we have these customized binders, and they're very useful in that they make the process more efficient because they are designed to do that. They have been made polymerized in a certain way just for this purpose. They're not like polypropylene, which happens to work because it's a plastic most of its life, but in some cases it can work in this context. Here, however, they have polymers that are designed specifically for this, and they are binders about which we know very little. And the reason why is that companies make these things, and they spend a lot of money developing them, and they turn around and they sell them to companies for a lot of money, because in the end, you have increased materials costs, but you decrease the energy costs downstream. So if you're a manager of the process, you look at this as a positive. So we don't have to run the furnace as long, we don't spend as much time or pressure or energy, and so that means that we can turn around and we're happy to pay an increased cost for something that's not polypropylene. Okay, and so this is what drives industrial decision making. Is this need to make things that are as cheaply made as possible, but still have the appropriate properties. And as I said before, we'll never know the structures of some of these binders because the companies they don't patent it, and it's considered a trade secret. Anybody know why they would never patent it? It becomes public record, yeah. And why is that a bad thing necessarily? They can what? If they buy the patent, they can use it. Yeah, right. What else can happen?
After 10 years,
17. Yeah.
17 years,
yeah.
Anybody can use it.
It does expire. The other aspect of it, though, is that these are polymers and they're additives in the process. And when this part finally comes out at the end of the furnace process, there's no evidence that polymer was ever there. So I can turn around, and if I know someone who is unscrupulous enough, I can pay them to make this polymer structure, because now I know what it is, and sell it to me, and I can use it in my parts, and no one will ever know, because when I turn around and sell these injection molded femoral heads, there's no evidence that that polymer was ever there. All right, and so this is why we have trade secrets, because stuff like this can happen, and it's true for a lot of processes where an aid in the process is no longer there in the final parts. You can never persecute someone, or prosecute, I guess, for patent violations as a result. Okay, so it's just the nature of the game. All right, so goals and challenges here. We need to remove the binder in the shortest time possible. Again, time is money. All right, and with relatively little impact on the structure of the compact, we'll talk about some of those structural impacts. The component can become very fragile until sintering begins. All right, and so we know why. We just talked about it. The fact that these beads are not mechanically interlocked and they're also very heavy means that gravity can pick them off very easily. You can starting with the outer shell. You can just start removing particles from the surface of this compact because they'll just fall right off. And so no chemical bonding, relatively little frictional interaction, and handling emotion becomes impossible. So you would put it into the furnace and walk lightly around the furnace during the run because it's at its most fragile at that point. So vibrations and things like that can literally tear your parts apart. And what we're going to talk about, though, is using a variety of newer processes. Final binding ideally occurs as part of heating immediately prior to sintering. All right, so you have at least a two-phase system, and one of those phases is wax, and you remove that, and that's the majority of it is wax. You're left with these nice capillary force generating pendular bridges between all your particles, and those just sit there until the particles themselves start to sinter. And of course, then the strength goes way up. But until that sintering process begins and you start actually forming grain boundaries between these particles, you rely on that polymer to hold everything together for you. And it might not be, it could be the carbon breakdown products of polypropylene at that point, but it's still holding everything together, all right? And sintering kicks off. So that's the general trick that people play here. And so we have these different debinding techniques, a lot of which we talked about. So thermal debinding can be enhanced by diffusion in a vacuum. This extraction or immersion technique is very popular in this context because what we can do is use a solvent to remove the wax. So we'll take our parts, we'll dunk them in a bath of heptane or hexane or something relatively cheap, and then the wax dissolves into that, but the polypropylene stays behind. High molecular weight, not soluble in heptane. All right, and so it does what it needs to do in terms of forming those bridges after all the waxy structure has been dissolved away. And so it's only running at whatever it is, 50 C or something like that, relatively low temperatures. Okay, and there's also issues with stirring and circulation and so forth that can speed this up. But it is a relatively low cost, could be lengthy, but relatively low cost technique. We think about permeation atmospheres, what can go in and remove these binders. Supercritical high pressure involves CO2. All right, and so CO2, I mentioned this once or twice before, especially at high pressures like it's like 40 degrees C and 80 bar, I think, or 80, is it 80 pascals? No, 80 psi. And yeah, anyway, so it's moderate temperatures and pressures. CO2 forms a supercritical liquid, and that liquid can dissolve pretty much any organic you can think of. All right, and nowadays this is very common in the dry cleaning industry, which back in the day used to rely on carbon tetrachloride to do the same thing. They would literally treat your clothes with carbon tetrachloride, which is a carcinogen. Not that that was the issue, but just having to deal with carbon tet was a problem for the people who worked in these companies. And so now instead of that, we use high pressure CO2, which turns into a nice gas and is completely harmless. All right, but it does the same thing. It dissolves organic-based compounds really efficiently. We also have something we've talked about, wicking processes. Again, this is all in the category of thermal. We can also think about condensation processes in which we generate a vapor and that vapor is removed. And we can catalyze this, so we can infuse an atmosphere of nitric acid, not liquid nitric acid, mind you, but vapor containing nitric acid vapor that diffuses in and attacks that polymer and starts to help break it down in a controlled way. So you make a polymer that's susceptible to nitric acid, and then so that goes in there and tears it apart at relatively low temperatures and pressures. Okay. Now you can't do this with everything because, especially for aluminum-containing alloys, nitric acid and aluminum do not get along. All right, so you have to be careful you don't dissolve or attack the metal. And then, of course, probably what the least preferable technique is oxidation in air, because especially with metals, you're going to oxidize your metal. All right, so you can only use that to a limited extent, if at all. All right, any questions about that? So we know where we need to go. We have some idea of how to get there. And we can look at a lot of different techniques. This is very hard to read slide. So I'll just go through this quickly. Solvent immersion, extracting the major binder phase from these materials, supercritical extraction, pressurize the fluid above the critical point to dissolve the binder into the liquid. Again, so it's a low temperature process. We're not relying on high temperature furnace treatment. Can you read any of this from where you're sitting, or is it total fuzz? Okay, sorry. Yeah, I need to work on that. Solvent vapor, holding compact and heated vapor solvent to absorb the major binder phase. Catalytic depolymerization, so you cause breakdown of the polymer in a controlled way. And then this is a low pressure system to use a gas to remove these components, the vapor components. And then passing gas over this is called the permeation controlled thermal process. Wicking, we've talked about that, throwing things into a packed powder bed and wicking them out from that. And then probably the least preferred in the metallurgy area, heating component air to simultaneously burn out the binder and oxidize the powder to give strength, which is not something that we want to do, but hopefully you can read that in your notes and just go through it and sort of make sure you understand the advantages and disadvantages, which are usually pretty obvious. Okay, and so again, getting back to where we like to go with a system that gives us what we're looking for in this rapid debinding process. Again, we have a multiple component binder system. So more than one, certainly. So at least two, it might be more than that. All right, we tend to talk about simple systems, but more real systems may involve multiple components. And so what happens is the binder progressively exits such that sufficient polymer remains after the first step to hold the particles in place using capillary forces. And so what we're doing is we start with this compact containing these nice round particles, and this is where theory and practice pretty much echo each other, because these nice round metal particles, we start to remove some of the surface phase, and in doing so we're generating vapor, and then that vapor has to reach in and start removing at a deeper level, all right, where things become more challenging because there's less oxygen, for example. You can also develop pressures. You can create conditions for carbon formation if you don't do this correctly. But what we're also hoping to do is see these bonds form, or at least be maintained between the particles, to help hold everything together in the right way. And so this gives it that very critical strength during the initial debinding. And this is sometimes called the backbone polymer, which is kind of confusing because the backbone of a polymer is the carbon-carbon bonds that run along lengths of that polymer, but we call these backbone polymers because it's the backbone of the compact. It holds it together. It gives it the initial strength and the critical strength inside the furnace as well. All right, so it's sort of the backbone, because the particles by themselves have no effective bonding between each other, so they are the weak link in this system. The polymer is what's holding everything together, maintaining the shape, and ideally keeping the structure in place as well. And so that backbone polymer is degraded and evaporates during the pre-sintering process. I have a nice movie to show you guys that sort of illustrates that really well. And if you have too low or too high polymer content, it can carry risks. And so we want it to be removed. We want it to leave at the right time. And the issue here is that we're talking about metals. And so with metals, we have again, an easy thing about metals is that they can absorb carbon when everything is said and done. So the Cindernex can form, and it can also gobble up the carbon, put it into the metallurgical structure, and generate carbides, which has advantages in terms of properties, as you guys now know. It'll stop dislocations from moving. And so, but you can do this. You have to make sure you don't do too much of it, all right? And you have to do enough of it because you want your compact to have the critical strength it needs. All these things have to be taken care of. With ceramics, 0 carbon is tolerable, because in ceramics, the carbon will sit there at the grain boundary, and it'll just be like oil and water. The two grains that are on both sides of that carbon are literally seeing no strength because carbon is totally incompatible with those alumina and zirconia, you name it. It's a huge weak point. So we have zero tolerance for carbon with ceramics. We have a very high tolerance for carbon with metals. Any questions about that? If that makes sense. So the component first removed should constitute 30% or more of the binder, and as it says here, can be as high as 98%, and probably in general it leans towards that because you don't need to leave a lot of polymer behind to make those necks. You do need to have a certain amount, but 30% is pretty low in the scheme of things. So typically you want to remove a lot more than just 30%. And what they do is work with oils and waxes. All right, a very familiar sounding name for very familiar sounding components: beeswax, carnauba wax, paraffin wax. Things that were around 100 years ago or more are used here. All right, some very old style materials make for nice cheap components that can be removed relatively easily, and if you want to work at it, then you can easily precipitate your wax out of the heptane and recycle it and put it right back into the process. And so if you're willing to invest, you can have a zero waste process, at least in terms of the waxes that are involved in these systems. And again, you can have 2/3 of the phases. Common backbone is polypropylene, so we pick on polypropylene a lot because it is one of the cleaner systems to work with. And so an example of this that makes use of that, and there's a variety of ways of doing this, you can have oil and wax that are part of the injection molding batch along with polypropylene, and this can be then put into some type of solvent-based wicking system that draws that liquid wax out. But the polypropylene is not a liquid at those temperatures, and so you have to go to higher temperatures, in this case to get the thermal degradation. All right, so you can just suck this liquid out, and it says oil. It's relatively high viscosity oil, trust me, but it is an oil. That comes out easily when it sees these porous surfaces into which those liquids can flow. And so we have a difference in that the wax removal is liquid flow, polypropylene removal is gas flow. All right, different temperatures, different phenomenon, but when this is present in very small amounts, you don't have to do the whole force flow thing. You don't have to pressurize your component anymore because it's sitting there and it's wide open pore spaces. It's easy for it to come out, and there's not much of it. Okay. And so we refer to this overall process as perforation of the organic component into that pre-existing metal injection molded microstructure. And hopefully that's a good name in your eyes, because you have a continuous organic phase at the beginning, and it perforates and leaves enormous pores behind. And that's a perforation process. It goes all the way through the organic component. And the only thing that's left are the polypropylene bridges in the pendular state, all right, where they can exert maximum stress. Does that make sense? All right. And so this process relies on surface connected pores. All right. We do know already that pore size varies with particle size. Smaller particles give us smaller pores. Things can be more difficult. The pores are tortuous, but they should be totally interconnected. And this is just sort of showing you what this looks like, in that we have groups of particles, we have vapor being generated, we have liquid that is turning into that vapor, and then ideally what we're doing is generating, ultimately, these pendular bridges in between small areas of these different particles. All right, so you notice that a lot of that liquid, that gray liquid, is not doing anything for us in terms of capillary pressures. But when there's a very small amount of it, that's when it starts to work. All right, so the funicular state is useless. The saturated state is useless. We need those pendular bridges that are only going to exist when the very small amount of liquid is left behind, and that liquid is polypropylene or some other much higher molecular weight polymer. And so because that's all going on, there's a lot of porosity, they're interconnected. The binder has to travel a distance significantly greater than the bulk thickness. This is typically, here we're talking about thermal degradation, in that we make gas, but the gas doesn't have a straight line to the surface. It meanders around and goes here and there and everywhere, so it can travel quite a bit before it actually leaves the compact. All right, so it's driven by pressure and concentration, but it doesn't make a beeline to the surface. It follows this tortuosity around for some distance. And debinding for both the vapor and liquid phases can be interconnected. The liquid resists displacement with the vapor. Each fluid is forced to establish its own tortuous flow channels to the surface. So what that means is, if we have more than a two-component system, all right, we can have more than just one perforation process. We can have an initial perforation in which binder A is removed, or wax A, and then wax B is removed, and a different set of perforation occurs, and then you have the polymer C, the binder C, that is finally removed after both of those two perforations have taken place. All right, so this is kind of how these systems can work. Amazingly, they still make money with all these processes. A lot of that has to do with the fact that the initial components, the waxes, are relatively cheap. All right, and so, again, to review, we have saturated, funicular, and pendular, and this is where we want to be in terms of creating strength. All right, these other two, it's just liquid and solid together. There's some rule of mixtures strength associated with that, but in the pendular state, we actually do get high values of strength in the system, not in the other two, even though it's kind of counterintuitive. But a lot of liquid is bad. And so what we see is this funicular first, following the saturated state. The backbone polymer remains in the pendular state. And that's what you're not seeing in this cartoon, is the fact that this gray liquid phase around it is not just one organic. All right. In the end, you're leaving the higher temperature polymer behind, and the capillary force attractive at binder contents well under 20%. 20% is actually pretty high. It's usually much less than that in terms of what's giving you the maximum capillary forces. And so, capillary forces can work with us in this context. Other times they work against us, but in this case, they're doing good things. And so this is showing you an SEM of stainless steel powder. And so a minute ago I showed you those glass spheres. These are stainless steel powder spheres. They're all spheres. Everything looks wonderful in this context. And it's showing you stainless steel, which is a very popular thing to injection mold, unsurprisingly. After first stage debinding with residual binder B in the form of pendular bonds at particle contacts. And so if you go back to that slide showing you the glass particles, you can see the similar things here. You've got these, first off, you can kind of make out the pendular structures themselves between some of the particles, but it's even more obvious when we look at where this microstructure used to contact itself. All right, you can see these rounded areas, and these result from the fact that this was continuous when we broke it open to put it in the SEM until we broke all those bonds, and now we can see the remnants of those bonds left behind by the successful removal of one organic phase and not the other. All right, does everyone see that? And so this is doing exactly what it should be doing in this context, providing those bonds, holding these things together. All right, so that's where microstructure or density is being favored by capillary forces, but this is an example of where other things can happen. And so what we've got in this first slide, at the 10 micron bar, we have a relatively decent looking microstructure. So we have coarse particles, we have fine particles that are somewhere in the 1/7 size of those coarse particles. There's a lot of them there, so this is a pretty high concentration batch. All right, and we have in this context a bunch of binders still present, and so what we're going to go do is start removing that binder from the system. And when that process of binder removal happens, these pendular bridges can form and they can move particles around. You've seen this already. We talked about liquid phase sintering, where you like that to happen. It pulls structures in and gobbles up porosity, right? That's a good thing. But what can happen here is a not so good thing as we heat this up. And so what's happening, first off, let's go back to this one. Here you've got, and this is one of the things you start to obsess about. You've got pore sizes, in the 1 to 2 micron range, something like that, maybe bigger than that in this structure. All right, you do have pores present, small spaces between those metal particles, which can ultimately control properties. But what happens is we heat this up, and all that liquid starts to move around prior to volatilizing out. And when it moves around, it moves the microstructure around too. It pulls particles together. So this is the biggest example. It's whatever that is, a 50, 60 micron pore that wasn't there in the left-hand microstructure. So the left hand, with the inappropriate levels of heating, for example, would lead to the right hand. Right, so the liquid forms, it pulls particles close together. It doesn't mean that everything is being pulled. So what happens is the microstructure retreats away from itself. Or it's being pulled apart. And you might think, well, maybe sintering will fix this. No, sintering will make it worse. So these areas will pull toward each other during sintering, and that pore will become even larger as a result. So you catalyze the pore formation because you don't control capillary forces, and things just get worse from there. Now, sure, yeah, if you stick it in the furnace for a long enough period of time, you might be able to eliminate those large pores, but it's more time and money to do that. All right. So better to make this microstructure behave and not turn into that microstructure. Does everyone see that? So it's not just density is what I'm saying. These could have similar densities, but you've rearranged the matter on the interior to generate pores, flaws that can lead to failure of the part downstream. Okay, so sometimes capillary forces are not our friend. And so we have this process of particle migration and agglomeration during debinding. Capillary stress from the pendular bonds, which a minute ago were doing good things for us, pulls particles into clusters, which is a bad thing. Solvent debinding followed by thermal debinding. Low density regions are pulled apart by regions of higher density, and you end up generating large pores or even cracks. Of course, a mitigating thing is that if you have the highest initial solid loadings as possible, that should help prevent this phenomenon because things can't move around when they're very tightly packed. All right, but this may only be 60% or something like that. It's pretty good in terms of density, but not high enough to prevent particles from moving around. So they spontaneously rearrange to higher densities internally than the overall density was initially. Any questions about that? All right, so these surface-based phenomenon can do different things. And some of those things are good, and some of them are not so good. Okay. And so this is a popular area to use this wicking process, in which we contact the metal injection molded component with a porous substrate, meaning that it's sitting in a bed of alumina, which is not a bad thing to use with metals. And that alumina contacts the surface of the part, and that surface consists of, as it heats up or is exposed to a solvent, a liquid, and that liquid can be wicked out into that surrounding alumina particles. So again, we're using capillary forces for good in this context, and they transfer liquid from one solid to another solid that we care less about. So we're basically pulling liquid out via capillary transport. This sponging action, which is a good way of describing it, carries the binder out. We still think about progression in leaving pendular bonds behind, all right? And so they are not connected because there's so few of them, all right? They're not a continuous phase. But eventually the liquid transport stops, and then you turn around, you take the part, shake it out of the bed of alumina, put it in the furnace, and then remove that small amount, again, polypropylene, picking on polypropylene, that small amount of polymer using the furnace. And the state that you want to get to is what's called irreducible saturation, which has that remainder of next behind. Solvent extraction is popular here. It allows full debinding. It can be a bad idea since the remaining powder mass will have no strength, so you have to make sure when you do this you have a solvent-insoluble binder that is not leaving with the other phase. You dissolve the wax, not the polypropylene. All right. So it's important that, yes, you can do this. It's a better way of doing things than capillary transport, but it also needs to be carefully monitored. And so this is just showing you a thermal version of that. And the important thing is here at the end, you have internal evaporation, and you've got what we like, which is a bunch of necks between all these particles. Now what you can start to see is that you go toward the surface, and this is where old and new kind of collide, and that you're starting to see full removal of those necks. All right, and that would be a bad thing All right, you could, if it's heavy particles, the marbles will just start falling off the pile. All right, and you start to shed particles on the floor of the furnace because there's nothing holding them to the rest of the compact. Whereas the interior might still have those capillary necks. So in a successful system, those capillary necks will be the same everywhere at the conclusion of that particular point in the process. Hopefully that makes sense. Okay. So then we go into something that's a little more detailed and kind of follows from that, in which you're talking about thermal debonding. The binder first evaporates from the surface. Binder flow rate to the surface is fast initially and is controlled by the rate of degradation. Pores open as the things perforate, of course, but near the surface this is favored since the molten binder continues to flow fast enough to feed the process. And what we're going to do is look at this figure 7.9a through E to look at binder saturation versus depth profiles. All right, so what we're showing you here are two somewhat idealized graphs, and we're looking at, again, thermal degradation of binder from an initially saturated structure. So we start with metal particles everywhere, polymer everywhere, no pores at all. We start heating this up, and we have a relatively high rate of debinding because the surface is exposed to the hot portion of the furnace, and that doesn't have far to go, so the polymer starts to leave this relatively quickly. We plunge below the surface. We still have a lot of vapor transport, so the rate of debinding is still relatively high, but then as we start to get down below the surface, then it slows down because diffusion is now controlling this overall process. We've removed the easily removed stuff at the surface, and now what is still left has to turn into vapor, and that vapor has to slowly make its way out of the compact. All right, so we slow down the overall process and then start to continually remove this, eventually to the point at which zero binder is left behind. But you also have this geometric effect which kind of follows that. We have three different areas that we're hypothesizing about: the surface and the center and points in between. And we're looking at this issue of pore saturation. And initially, everything is saturated. We have binder everywhere. And then just think of it as a big block. And the surface is going to consist of easily removed polymer. But then we go to state B, where we're down below the surface now. Things are slowing down. And then from there we go to C, and we have even less pore saturation going on, more of this process of going from funicular to pendular. And then as we get below the surface even further, we're looking at remaining polymer, whereas what's out here may be polymer free, or at least wax free. Maybe we have the polypropylene left behind doing what it's supposed to do. And then in the center we can end up, the very last portion of it, that E state shown over here, is going to be the center where we still have the binder left behind because of its distance from the surface. All right, this is not the ideal case, but this is the kind of thing that can happen with these organic containing systems. Does that all make sense? And so it goes from this 2D structure to thinking of it as what it really is, which is a 3D structure, which consists of depth and distance, and those factors can factor into this debinding process. All right, and so it doesn't happen everywhere at once. You guys heard the shrinking core model? Maybe not. All right, so this is an example of the shrinking core, where it's just shrinking away and the core ends up being different from the outside. And that's what's essentially happening here. Any questions about that? Okay, so I got this movie, which I'm going to show you first. It kind of summarizes a lot of this and goes a little further than that. So this is it's got this Chariots of Fire soundtrack that goes with it. So in the recording you probably won't be able to hear me talking, but let's just go with it here. That stupid noise. So obviously these guys make a lot of things, sintered metals and so forth. and what we're looking at here is the process of production from their eyes, and it's surprisingly well done in terms of what it shows you. So we have the base powder, we have the alloying elements, and they're going into this mixer, and that is mixing the two powders together. All right, so this is not hard to do. There's a bunch of marbles, you just mix the marbles together, boom, you've got the right overall alloy, at least in terms of the powder itself. But then you come along and you take that and you pour it into this what's called a kneading process, which, as you'll see, uses these Brabender type colors, and you bring in the polymers. All right, so this is showing you the high temperature polymer phase, and then the lighter looking bag is the wax. Now in reality there'd probably be 5 bags of wax and 1 bag of polymer, maybe 4 bags of wax than that. And so this is then sheared. You guys know about the shearing process now. This looks very familiar to what you've seen before. Very large batches being made with this process, so we're mixing the organic phase as best we can with the metallurgical phase. And then the result, ultimately, this is, by the way, so this is the target geometry. We're trying to make some sort of mechanical component there. Maybe it goes into a car. Maybe we need to make 10 million of them in a month. All right, and these are the 2 platins that come together to make 1 part or more than 1 part. In this case, 2 of the same parts, all by this injection molding process. And so we have the injection molder itself, which we talked about now, in which those platins are located. And so we're going to utilize that type of structure, and we have these pins holding everything together, also help take it apart. And so we bring in all that pre-mixed organic multi-binder component. We go through the extrusion process, which is mostly friction to heat this up and turn that into a continuous red pool of material. So it goes from being lots of trapped air to being 0 trapped air when that final red fluid is ready for injection. So then injection mold the darn thing, this part is made, and we talked about how long this takes previously, a couple of seconds to actually make it. Everything else can be much longer than that. And then this is popped out, and you see the runner and the gate material that has to be attached from the part itself, and the process repeats itself as quickly as possible. Just trying to make money. And again, you can have, as you saw, you could have 2 of these being made at once, you could have 6 of them being made at the same time. Really, more than 1 at a time. And then we go to the furnacing. So you paid someone to take off the runners and the gates, the screws, and then they bring them over and they load them in the furnace. A nice neat line in this case, even more than that in reality. And so you see the initially debinding stage in which we're looking at removing the wax, and we'll see that in a minute here in more detail. And then what's left behind is the polymer. So this is what it looks like post-injection molding, bathing in liquid. That liquid, most of which is wax, is removed, but you leave some behind, and that's the polypropylene, the glue holding everything together, without which nothing happens. And from there, it goes into the higher temperature stage, and this is where the tricky trade-off happens. You see it shrinking. It's a nice movie. Really gets a lot of stuff across. So ridges are left, things heat up, and they start to sinter to each other. But that ridge turns into carbon at the right point just before sintering happens. All right. So you capture the process of sintering while maintaining the overall shape. In the end, everything looks wonderful after it goes through the cooling process and comes out the other side. All right. So, you know, the real industrial process looks very similar to this, except bigger and more parts. You could be running 100 parts in at once. Those kinds of things are all going on in this process of injection molding. All right, any questions about that video? Does that make sense? It pulls a lot of stuff together. It's very nicely done. And so this process of, a question? No? Okay. Questions about carbon residue? We know we on some. Bless you. It's tolerated by some alloys. It can be disastrous for others. The carbon can have effects on mechanical, corrosive, magnetic properties. Now, sometimes we want the mechanical properties. All right, carbides help us there. And so other times they can really downgrade the corrosive abilities or the ability to resist corrosion, and they can have up and down effects on magnetics. Stainless steel, titanium alloys, cobalt chrome, all these things can either benefit or be degraded by the presence of carbon. Some binders can add up to 5% carbon, all right? And so you're not throwing carbon powder into the system to make carbides show up in your system. You're throwing polymer in there with a known degradation capability and producing different amounts of carbon left behind that you want, that end up being part of the metallurgical structure. In other alloys, very low carbons are tolerated, like stainless steel 316L. You want to have extremely small amounts of carbon in stainless steel 316L, which is kind of the de facto surgical standard for stainless steel. And so it varies depending on what you're trying to make. You can only tolerate so much in the way of carbides in that particular steel. And so you want complete binder removal without residue. Can be very important for some systems. Again, you can have much higher levels or much lower levels. And the propensity for carbon deposition under inert atmospheres varies with the polymer used. And this is one of the things that still doesn't make a lot of sense. This is showing you a very simple experiment. These are not injection molded polymers. These are just polymers heated to 1,000 degrees C in an argon atmosphere. So you can do this in the TGA. So you have just a little chunk of pure polyethylene, and you see what it does in terms of weight loss. And so when you do that for polyethylene, again, this is an argon. All right, so no oxygen to oxidize the carbon to anything. What forms gives you solid carbon, and that's what you're looking at here in terms of this residue, is solid carbon. Polyethylene 0.11, polyisobutylene 0.10, polypropylene carbonate 0.10, polymethyl methacrylate 0.22, goes up a little bit. All right, so that oxygen is making the amount of carbon left behind go up, which seems backwards. Polyethylene oxide, which is a really weird one. So polyethylene oxide is just polyethylene with oxygen in the chain, repeated over and over. And so you look at this and say, wow, that's a lot of oxygen, all right? But it actually leaves a lot behind under these circumstances. So that oxygen is not helping us in terms of causing it to volatilize in something that can be easily removed. Polyvinylbutyrol, similar thing, it's got some oxygen in it. And then methylcellulose, which is one they used a lot in looking at the early days of injection molding, leaves a large amount of carbon behind. It makes some sense because it's kind of a three-dimensional polymer structure. Okay, and so knowing what you need in terms of the carbon content that you're shooting for may dictate which polymer you choose based on how much carbon it's going to leave. You can have too little carbon in these systems, all right, and a degradation in your properties as a result. So you have to keep that in mind. Oh, okay, so last slide. During thermal debinding, as we discussed many times, the compact is weak, which are marbles. Capillary stresses generated by gradients in binder distribution can cause warping or cracking. A cycle or furnace that successfully processes large tungsten powders might not work for 0.4 micron alumina. All right, this should not be a surprise to you. Rapid thermal debinding is disastrous for shape retention, and strength varies dramatically during the process. And the key thing here, first off, so we have this kind of approximate plot, and we're looking at strength versus percent binder. And so we start here relatively low, and as we start removing that binder, it reaches a maximum. What exists at this point? Why is it a maximum? It's the same particles. What have we maximized? What? Exactly. So we made the capillary forces as strong as we can possibly make them. So it's strong because capillary forces are making it strong. All right, so we know it's not it is the pendulum state, it's not the funicular or saturated state. And then from there we move on, and so we're removing more and more of this, but what we need to see happen is this trade-off. So the metal says, oh, I've got it from here, and the polymer turns into carbon, and then the metals start to sinter, and the strength goes up really a lot more than what's shown here, because you're sintering it now, so it's much stronger in the end. But this area of trade-off between the polymer and the metallurgical phases needs to be controlled very tightly, otherwise your compact can fall apart. Okay, any questions about all that? All right, I'll see you guys on Friday, right?